Why didn't Jupiter become a second sun? Simply because it doesn't have enough mass to ignite nuclear fusion. It fell short of the threshold needed to burn hydrogen. Instead, it silently radiates the leftover heat from its formation. But here comes the question. Where does that continuous internal heat come from? And what drives the violent atmosphere on its surface? Today, let's journey up close to Jupiter and uncover the mysterious forces beneath its dazzling skin. As you approach Jupiter, its face appears like a shattered mirror, splitting into bright, swirling cloud bands before your eyes. The brown belts and pearly white zones stretch across its equator in intricate, serpentine patterns. These aren't just decorative stripes. They are living traces carved by powerful jet streams racing through the atmosphere. These high-speed air currents encircle the entire planet like raging dragons. Jupiter's atmosphere is organized into alternating bands of eastward and westward jets, forming distinct rings that race from the equator to the poles, with wind strength increasing layer by layer. In the bright zones, ammonia clouds rise from the depths, reflecting sunlight into soft white and pale gold hues. In the darker belts, we can glimpse deeper atmospheric layers. The clouds here are tinted reddish-brown and amber by compounds such as ammonium hydrosulfide. Each belt flows opposite to its neighbor, creating a breathtaking masterpiece sculpted by raging winds. The jet streams here can reach speeds of several hundred kilometers per hour, far exceeding any hurricane on Earth. In the upper atmosphere, some jets can even exceed 650 kilometers per hour. Driven by the Coriolis force from Jupiter's rapid rotation, the entire atmosphere is torn into alternating east-west jet streams, separated by bands that look like shimmering silk ribbons. Beneath this intricate pattern, the planet's internal heat drives massive convection cells, regions filled with rising warm air and sinking cool air. This internal heat continually fuels the deep convection, powering the unending dance of Jupiter's atmosphere. Though the jet streams appear clearly divided, their boundaries are turbulent. Fast-moving air masses twist and roll at their edges, forming wave-like patterns and spiraling structures. Ammonia and water vapor rise from the depths, condensing into bright white cloud bands, while descending air creates transparent windows into darker layers below. Jupiter looks like a living marble of color, boiling, swirling, and endlessly flowing in silence. And hidden among those endless stripes lies the solar system's most legendary storm, the Great Red Spot. This enormous orange-red oval has been raging in Jupiter's southern hemisphere for centuries. Its size is vast enough to swallow the entire Earth in one gulp. Technically, the Great Red Spot is an anticyclonic system, a massive high-pressure vortex spinning counterclockwise. It towers high above the surrounding cloud tops. Up close, its cloud deck appears dense and layered, colored like weathered brick, with a faint red haze hovering above, giving it a haunting glow. Even today, scientists are uncertain what gives it its hue. Perhaps complex organic molecules or compounds dredged up from deep below. Inside the vortex, bands and spirals intertwine like a colossal eye, constantly rotating. Winds at its edges reach speeds of up to 430 kilometers per hour. So powerful they twist the clouds into surreal, dreamlike shapes. Since it was first observed more than 150 years ago, the Great Red Spot has remained one of astronomy's enduring fascinations. Around its rim, white clouds roll and churn, some being pulled into the vortex, others thrown out. Smaller storms often approach it. Some get flung away, others are devoured whole. The Great Red Spot doesn't just dominate its own territory. It influences weather patterns across great distances. Yet in recent years, scientists have found that this roaring giant is slowly shrinking. Its diameter is now only about half of what it once was. Even so, it remains the largest storm in the solar system. It rotates once every 6 Earth days, with its center surprisingly calmer than the edges. Above this immense fortress of swirling gas floats a faint red canopy, separating it clearly from the surrounding bright zones. Occasionally, flashes of lightning illuminate its depths, briefly cutting through the night. Data from the Juno spacecraft shows that the Great Red Spot isn't as deep as once thought, but it still rises tens of kilometers above its surroundings, a towering gaseous mountain in Jupiter's vast sea of storms. And it is far from alone. The entire planet is covered with countless smaller vortices and storms. Along the jet streams, strings of white ovals appear, smaller anticyclonic storms spinning counterclockwise like miniature versions of the red spot. Some of these small storms last for decades, while others fade quickly. In 2000, 3 white ovals merged to form a new, larger storm known as Oval BA, which later turned red, nicknamed the Little Red Spot. It's about half the size of its legendary sibling. Between these storms, fast-moving jets pull the clouds into long streaks and rippling waves, some forming Kelvin-Helmholtz patterns. The same wave-like motions that appear when air flows at different speeds shear past one another. In some regions, dark brown barge clouds drift slowly within the jet streams, while bright, popcorn-shaped cloud clusters mark regions of intense convection. Since Jupiter lacks a solid surface to block them, these storms can extend deep into the atmosphere and last for astonishingly long periods. Looking across Jupiter's curved horizon, you can see everything from tiny whirling eddies a few hundred kilometers wide to chaotic turbulence zones where multiple vortices collide, a grand symphony of moving air. Behind the Great Red Spot, the atmosphere becomes especially turbulent, filled with swirls and pale clouds where new storms are being born. Yet beneath this surface chaos lies an underlying order. Every storm is locked firmly into its latitude band, tethered by the powerful jet streams that prevent them from drifting away. If you fly over Jupiter's poles, you'll witness an extraordinary sight. At the North Pole, 8 gigantic cyclones encircle a central vortex, forming an almost perfect octagon. Each cyclone spans between 1,500 and 2,800 kilometers, positioned so close together yet maintaining independent rotation, an astonishing display of balance. Each one spins counterclockwise, their arms interlacing like a geometric dance of nature. The South Pole mirrors this marvel, initially featuring 5 cyclones before gaining a 6th, forming a striking hexagonal pattern. These polar storm clusters have remained remarkably stable for years, barely changing shape, evidence of complex underlying physics. Perhaps it's the fluid dynamic equilibrium among the vortices, or the powerful jet streams maintaining their structure. And just when you think Jupiter has shown all its cards, lightning strikes, a brilliant flash cutting through the polar night, bathing the cloud tops in silver light. This lightning isn't ordinary. It's a surge of immense energy. Jupiter's lightning storms are far more powerful than Earth's. As early as 1979, the Voyager spacecraft captured brief, dazzling flashes high in Jupiter's atmosphere, humanity's first glimpse into the electrical heart of this gas giant. Initially, scientists thought lightning occurred only in the water cloud layers deep below, where temperatures are similar to Earth's thunderstorm regions. But data from Juno revealed a startling truth. Jupiter also has shallow lightning in its upper atmosphere. These upper atmospheric flashes occur in regions as cold as -88 degrees Celsius, far below water's freezing point. Under normal conditions, liquid water would freeze solid. But on Jupiter, ammonia acts as a natural antifreeze, keeping water in a strange semi-liquid state. During fierce storms, hailstones are thrown up to 24 kilometers high into ammonia-rich layers, where they melt and mix with the gas, forming slushy mushballs. As these mushballs tumble through clouds of ice crystals and hail, they generate static charge through friction, ultimately triggering shallow lightning, electrical symphonies flashing through the ammonia, ice clouds, glowing in eerie blue and gold hues. Each burst lasts only milliseconds, but rivals Earth's strongest bolts. Deeper down, 48 to 64 kilometers below the cloud tops, traditional lightning storms rage on, with water existing simultaneously as vapor, liquid, and ice, just like within Earth's thunderclouds. Intense charge separation there gives birth to lightning many times stronger than any on Earth. Juno has detected thousands of such strikes, and even recorded their sharp radio whistles, echoing through Jupiter's immense magnetic field into space. The discovery of shallow lightning also solved a long-standing mystery. Why does Jupiter's upper atmosphere seem mysteriously lacking in ammonia? The answer: those ammonia, water mushballs, silently drag the gas downward, burying it deep within the planet's atmosphere. After each thunderstorm, lightning once again rips through distant clouds, illuminating towering convective columns. Immense storm towers rising 30 kilometers high, driven by Jupiter's internal heat. For a brief moment, lightning outlines their colossal shapes, like the hammer of a thunder god forging the planet's atmospheric world. If Jupiter's storms and clouds paint a portrait of chaos and grandeur, then its auroras are the crown jewels on that masterpiece. At both poles, auroras blaze with astonishing energy, radiating blue and violet halos like celestial fire. Unlike Earth's auroras, which appear only during strong solar storms, Jupiter's auroras never cease. Their energy is hundreds of times greater than Earth's, constantly draping the polar regions in an electric veil. These auroras aren't powered solely by the solar wind. Jupiter's immense magnetic field also plays a vital role. Its magnetic field, generated by the rotation of metallic hydrogen deep within, is 16 to 54 times stronger than Earth's. This vast magnetic force captures high-energy particles and guides them toward the poles. When these particles strike Jupiter's upper atmosphere, they excite hydrogen molecules, releasing ultraviolet and infrared light, forming immense auroral rings. In ultraviolet images, the northern aurora appears as a vivid electric blue spiral, swirling under magnetic control. Even Jupiter's moons join the spectacle, especially Io, the most volcanically active body in the solar system. Io constantly ejects ionized sulfur and oxygen into space, feeding Jupiter's magnetosphere with energy. As Jupiter rotates, these charged particles are flung toward the poles, intensifying the auroras. Io's footprint appears as a bright spot at the edge of the auroral ring, a tiny torch illuminating the magnetic bond between the moon and its planetary parent. Europa and Ganymede also leave their traces in these luminous displays. During periods of intense solar activity, powerful particle storms reach Jupiter, causing its auroras to surge dramatically, their glowing curtains stretching thousands of kilometers above the poles, far surpassing any aurora seen on Earth. Yet even if you could stand above Jupiter, you wouldn't see them. They shine mostly in ultraviolet and X-ray wavelengths, invisible to human eyes. These auroras are not just visual wonders. They are a cosmic symphony of electromagnetic power. Pulling back from Jupiter's blazing auroras and storming cloud seas, we find yet another hidden marvel: Jupiter's rings. Yes, Jupiter has rings too. But unlike Saturn's bright and majestic ones, Jupiter's are faint and ghostly, like spider silk suspended in space. They weren't even discovered until 1979. Jupiter's rings are thin, delicate, and nearly transparent, visible only when backlit by the sun. The main ring forms a glowing band around the equator, while faint, diffuse outer rings spread beyond it like wisps of cosmic dust. These rings exist thanks to Jupiter's inner moons, such as Amalthea and Adrastea, which orbit near them. Tiny impacts from micrometeoroids constantly strike these moons, ejecting dust that drifts into orbit, forming the rings we see today. The main ring's material comes mostly from Adrastea, a tiny moon only 19 kilometers wide. Farther out, Métis and Amalthea also contribute dust to the outer rings. Up close, these dust grains are minuscule, mostly micrometer-sized silicate particles that reflect little light, making them almost invisible in visible wavelengths. Only infrared or backlit observations can faintly reveal their presence. So, what kind of world is Jupiter truly? When you take in its churning atmosphere, its fiery storms, its thunder and lightning, its glowing auroras, its dusty rings, and its many loyal moons, Jupiter becomes more than just a planet. It is a living, dynamic system, a vast symphony in motion. Jupiter remains a burning monarch in eternal transformation, a mysterious giant that has carried the mark of the universe's ancient chaos since its birth, still telling, through its thunder and light, the unfinished story of the cosmos.